So, hello, welcome back to another episode of the Self-Development Tactics podcast, or the Me podcast, or the Me I'm watching videos podcast. Today we are going through another video another podcast episode. It is very, very meta, to be honest, having a podcast around podcasts. Maybe there's going to be a podcast around podcasts, listening to podcasts. Anyway, Dr. Nolan Williams, Psychedelics and Neurostimulation for Brain Rewiring, aka Therapy. Huberman Lab podcast, episode number 93, and Andrew Huberman, the Andrew Huberman Lab podcast. This is basically everything that I know. For whatever reason, I should actually check that out. I don't see the date, but I'll give you whatever I have there. There we go, there you see it. This is quite everything that I have, and we're gonna skip through a few of the things. I do not want to go through the whole one. I also do not necessarily find that too important in terms of, you can just watch the whole video by him or listen to the whole podcast by him. This is not what I should be doing. So it is basically about psychedelics and how they can be used for therapy. Let's see.
That you said I'd like to focus on a bit more, because I think we hear that the brain and the heart are connected, but you described, I believe, a direct relationship between areas of the brain associated with emotion and heart rate.
Yes.
And that makes perfect logical sense to me. But I think at the same time, many people out there probably think of the relationship between the heart and the mind as kind of woo or kind of a soft biology. But here you're talking about an actual physical connection between what area of the brain is it?
The first place for the stimulation.
I didn't know about that as well. So by the way, just just pointing that out.
Is called the dorsolateral prefrontal cortex. It's kind of the sense of control kind of governor of the brain. And then what we know is that when you use a magnet, use kind of what we call Faraday's law, this idea of using a magnetic pulse to induce an electrical current in electrically conducting substances. So in this case, brain tissue, but not skull or scalp or any of that, or hair. You avoid all that, just the brain tissue. Then you have a direct depolarization of cortical neurons, the surface of the brain's neurons in this dorsolateral prefrontal. And if you do that in the actual scanner, which we can do, you can see that distributes down into the anterior cingulate and the insula and the amygdala. And ultimately, the tract goes into something called the nucleus tractus solitarius, and ultimately into the vagus nerve, into the heart. So that the heart very consistently seems to be the end organ of the dorsolateral prefrontal cortex. If you measure heart rate in standard ways that cardiologists measure heart rate, and you stimulate over this left dorsolateral, you get a deceleration of the heart rate, and it's very time locked to the stimulation. So it's a 2-second train of stimulation. At 1 second, you see the deceleration. It goes down about 10 beats per minute, and then it'll drift back up, and there's a break for 8 seconds on the stimulation. It drifts back up, and the stimulation goes back in, and then the heart rate goes back down. And so you see the heart rate just do this, 10 beats per minute every train. And so we know if you do that over visual cortex, you don't get that, or motor cortex, you don't get any of those findings. It's really specific to this kind of control region of the brain. And so, it seems to, it's our work, other folks' work, Martin Arns in Europe, the Netherlands work, showing the same connections. I think it's been replicated like 4 or 5 times.
So you mentioned left dorsolateral prefrontal cortex. Anytime I hear about lateralization of function, I get particularly curious. Because obviously we have two mirror symmetric sides of the brain. There are rare exceptions to this, like the pineal and things of that sort, that are there is only one pineal. What is special about the left dorsolateral prefrontal cortex? Does this have anything to do with handedness, right hand or left hand? Because we know right hand and left-handedness has a lot to do with lateralization of function for language, a topic for another time. But why do you think the left dorsolateral prefrontal cortex would be?
Wait, does it make a difference? Does it make a difference whether I'm left-handed or right-handed in terms of my brain? So the question is, if this is the case, yeah. Still watching video will pause soon. I don't want that. If this is the case, is it a benefit for everyone that is left-handed? Or is it a downside? I would actually, for whatever reason, I don't know why, I would go for it is a good thing. Just because it is more rare. There are not that many people left-handed versus right-handed. Really interesting. Anyway.
Connected to the heart in this way.
Yeah. I think so. So left dorsolateral, is thought to be the side that when you excite it, when you kind of do excitatory stimulation, potentiating sort of stimulation, that you can reduce depressive symptoms. And a guy by the name of Mike Fox at Harvard has demonstrated that if you have strokes in the brain that cause depression, and you put them on the human connectome 100,000 patient map, and you ask the question what they're all functionally connected to, left dorsolateral. If you take lesions that cause mania in individuals and you put those all on the human connectome map and ask what they're all, the one common area they're all connected to, it's the right dorsolateral. And so there seems to be a hemispheric, balancing of mood between these two brain regions. And we know this from an experimental standpoint too, because you can take individuals with depression and you can excite the left, or you can inhibit the right, and they're both antidepressant. You can excite the right, and that's anti-manic in some studies. And so this idea that there is this hemispheric balancing of mood is quite interesting, right?
It's incredibly interesting. And just so people know, if you're curious what the connectome is, a connectome is a term that was built out of this notion of genomes being a large collections of sequencing and mapping of genes. They're proteomes of proteins, of connectomes as so-called connectomics of connections between neurons. So the Human Connectome Project is ongoing. And I find that incredible that within the Connectome Project, they can identify these regularities of right versus left dorsolateral prefrontal cortex, especially since I've looked at a fair number of brains from humans, certainly not as many as you have. And if you look at the architecture, the layers, the cell types, and even the neurochemicals of which cells are expressing, say, dopamine or serotonin, or receiving input from areas that make dopamine or serotonin, they don't look that different on the right and left side. And yet here we're talking about a kind of an accelerator and a brake, if you will,
that's right,
on depression and mania, using what, at least by my eye and I think other people's eye, look to be basically the same set of bits, the same parts list, more or less. So what gives these properties to the right and left dorsolateral prefrontal cortex? Is it the inputs they receive? Is this something that we learn during development, or do you think that we come into the world with these hemispheric biases?
Yeah, it's a great question. And it hasn't been worked out, which your original question was around, in a left-handed individual, which, as you know, 25% of those folks end up having a right brain dominance, or 1% of right-handed people have a right brain dominance if it's flipped, right? And that, unfortunately, that study still hasn't been done at the level, because that would be probably pretty helpful for teasing some of this out. But it's still being sorted out, right? We know enough to know this phenomenon exists because we can use TMS as a probe and do these sorts of manipulations. But to my knowledge, there hasn't been anybody that's gotten so interested in it that they've been able to get a mechanism of why that is. But it, it's kind of empirically true in the sense that you can push and pull on those systems, or in the case of strokes that folks have, and then you kind of get their brains and their brain images and look at where the strokes landed. Those kind of causal bits of information point to this asymmetry.
Interesting. Well, in that case, going with what we do know, that stimulation of dorsolateral prefrontal cortex slows the heart rate down transiently, but slows it down, and seems to alleviate at least some symptoms of depression. Leads me to the question of, why would that be the case? Is it does it tell us anything fundamental about depression, that anxiety is inherent to depression? I think a faster heart rate is, part and parcel with anxiety. In my laboratory, we've studied fear a bit in animals and in humans, and we often observe brachycardia, where somebody or an animal is afraid of something, and rather than the heart rate speeding up, it actually slows down. Something that most people don't think about or recognize. But given that stimulation of dorsolateral prefrontal cortex slows the heart rate down and can alleviate depressive symptoms, and that there are other ways to slow the heart down, I have two questions. What do you think this tells us about the basic architecture of depression and its physiology at the level of the heart? And does the circuit run in the opposite direction too? If one were to have or find other ways to slow the heart rate down, say with a beta blocker, does that help alleviate depression? Yeah,
no, it's a great question. So I'll answer the second question first. So we know that, and there are ongoing trials of this, if you stimulate in the vagus nerve, in an implanted vagus nerve stimulator, you can actually, have the afferent parts of the vagus, you project ultimately up to the DLPFC through the cingulate, through these anterior insula. So that obviously the same tract, right? And you can stimulate there and alleviate depression, which seems very unusual, right? You're stimulating a cranial nerve down in the neck, but if you can get up into the brain, you actually can improve depressive symptoms. And so, more evidence that this is a kind of a whole track and system. And if you stimulate in part of that system, it appears that you can.
Which for me sounds like, well, basically a track or a street with two lines. You're having one down the line and one up the line. So it actually kind of makes sense that I can go both ways. If my brain can go downwards, why shouldn't it also be able to, do it reversely? And what I find particularly interesting about that, what are the physical symptoms that I'm having, or that one is having, that is depressed? Could we, and this might be totally here about this, could we deal with it in the opposite way? I don't know. It might actually be very specific for certain people. It might be the case that some people are having a higher heart rate. It might be the case that some people are, of course, feeling worse, and but maybe they have abdominal pain and whatever. Just those signs, those ways in which depression shows itself. Besides, of course, feeling bad mentally. But then, what about, I don't know, when I'm having headaches, doing something about those headaches, can they then also, lead to just, feeling better about myself because I'm not having this issue, which, of course, kind of makes sense already. When I'm feeling better physically, I'm probably also feeling better mentally. But yeah, it's actually quite interesting. And I don't want to say obvious, but because I am no neuroscientist, I am no biologist, I'm doing my bachelor in fucking architecture, so it's something completely different. But yeah.
And improve mood.
What if I were somebody who did not have a stimulating electrode in my vagus nerve, and I was dealing with minor depression, and I decided I wanted to take some other approach to slow my heart rate down via the vagus? For instance, exhale emphasized breathing, or deliberately slow cadence breathing, things of that sort. Is there any evidence that behavioral interventions of those kinds can alleviate depression or some symptoms of depression? And is there any evidence that it does indeed feed back to the dorsolateral prefrontal cortex to achieve some of that alleviation?
Absolutely, yeah. So there's a number of studies implicating the dorsolateral in say, meditation, mindfulness, that sort of thing, and they're small studies, but pretty well designed studies suggesting that behavioral interventions in mild depression actually work quite well. There seems to be a volitional threshold for depression, where at some point you start losing it. You go from being completely in total volition to having kind of semi-volition. You have thoughts that you really have a hard time controlling and that sort of thing. And when you go through that threshold, at some point, it gets harder and harder for those sorts of things to kind of kick in and work. And the extreme form of that is catatonia, right? Where people in a very severe form of depression get kind of stuck motorically, right? And they obviously can't, they have no control. And so, or very limited control. And so, I think there's a threshold in which these sorts of interventions will work. Exercise seems to really be a good treatment for mild depression, and it may work through the mechanism you're describing, right? As we all know, athletes hold a lower resting heart rate than folks that aren't. If you were an athlete, you had a lower resting heart rate, you stopped, exercising, and a couple years later, your resting heart rate in many cases goes up, right? And so maybe that's part of the process. I'm not aware of any studies specifically looking at dorsolateral prefrontal physiology pre-post exercise, but it would be a great study. I think that would be really helpful to understanding this, especially if you had a correlation of changes and kind of lowering of, say, heart rate with mood improvements. There's been a lot of work with heart rate variability and depression, and studies are kind of point towards it. It's not every study is positive for this, but quite a few studies say basically that lower heart rate variability is associated with moderate to severe depression, and that may be part of that mechanism of that heart-brain risk.
So I'm both intrigued and a little bit perplexed by this relationship between heart rate and depression. On the face of it, I would think of depression as depressed. So lower heart rate might make somebody more depressed. You even mentioned catatonia, or somebody that just doesn't seem motivated or excited to do anything. Yeah. I think of mania as elevated heart rate and being excited. On the other hand, I realize that anxiety, which brings about ideas as elevated heart rate, is also built into depression. Which brings me back to what you said earlier, which is that when we say depression, are we really talking about 4 or 5 different
that's right.
Disorders,
that's right,
for lack of a better word? And for what percentage of people that have depression does some approach to reducing heart rate work? Whether or not it's stimulation of the left dorsolateral prefrontal cortex by way of transcranial magnetic stimulation, or by taking a beta blocker, or by stimulating the vagus. Can we throw out a number, a rough number? Does that help 30%, 50%? How long lasting is that relief?
Yeah, and to be clear, the deceleration of the heart rate is in the moment when the stimulation is happening, but it's not something that's necessarily maintained chronically. It's more of an indicator that you're in the right network more than it appears to be itself, central to the mechanism. The heart rate variability piece may be, and there's some studies that link the two, but the actual deceleration seems to be much more of a marker that you're in the right system. But it very well could be that the heart rate system and the mood system just sit next to each other, and the stimulation hits both. If you look at how much of the variance in the mood is explained by the heart rate deceleration, it's not a huge amount, right? So it only explains a small percentage, and so it's unlikely that simply reducing the heart rate, and in fact, for many years, propranolol and these sorts of drugs actually were implicating causing depression, and so that's been kind of debunked. But it's unlikely that simply decelerating the heart rate is going to improve depression. But what it does tell you is that if you're in that area that is the mood regulatory area, there's some parasympathetic cortical kind of process that's going on that gets in and causes this to happen. And it's independent of mood. You can take a normal, healthy individual and you can do this, and they're going to decelerate their heart rate.
I'm so glad you mentioned the parasympathetic nervous system, which of course is most people think of as the rest and digest, or the kind of calming side of the autonomic nervous system. As I'm hearing you say all of this, and in particular what you just told me, which is that it's not as if having a lower heart rate protects you against depression, or a higher heart rate is associated with depression, although at the extremes that might be true, but rather it's something about the regulatory network, the ability to control your own nervous system to some extent. And when I think about the autonomic nervous system, I like to think about it as a seesaw of, alertness and calmness. And when you're asleep, it's a lot of calmness. And when you're panicking, it's a lot of alertness and I don't think this has ever been defined. And when I teach the medical students at Stanford Neuroanatomy, my wish is that someday I'll be able to explain what the hinge in that process would be, right? Not the ends of the seesaw. We know what the sympathetic nervous system is and what it's to wake us up and make us panic or make us feel nicely alert and calm. We know what puts someone into sleep or a coma or makes them feel relaxed. But what shifts from one side of the seesaw to the other, and the tightness of that hinge seems to be what you're describing, that depression is sort of a lack of control over inner state, so that when I'm stressed, I can't get myself out of it. But when I'm feeling completely collapsed with exhaustion, I can't get out of bed and get motivated to do the very things that would help me get out of depression, like a workout or social connection or eat a quality meal, these kinds of things. So this is perhaps the first time that I've ever heard about a potential circuit for the hinge, as I'm referring to it. Does that make any sense at all?
Absolutely.
Okay. I just want to make sure that I'm framing this correctly in my mind.
Absolutely. And in some studies, if you do the same identical stimulation on the right dorsolateral, you can get an acceleration. Just kind of further confirming this idea of lateralization, right? That even it appears that even the prefrontal cortex, cortical areas seem to be lateralized in this way. And it's less. The right finding is more variable depending upon the study. The left's very consistent in this way. So
we've talked about transcranial magnetism.
And at least for me, that also makes it quite clear. I'm sorry for not talking that much and basically not being able to add something of value. But it makes it very clear then why meditation and mindfulness, and I would also say exercise, is so useful, also so important for the depression and depressive people, because what I see is, yes, meditation and mindfulness and probably every other way, every other maybe technique is so useful because you are able then to control your state, your inner state, a bit better. And I think this is the same thing with exercise, I would argue. And I'm just thinking, I've been exercising on a regular basis for basically my whole life, I'd say, whether it is riding my bike or working out and whatever. But I think breathing and heart rate, and when your heart rate goes up, when your heart rate goes down, and whatever, it is something I think athletes recognize, realize, and see. And again, I think they are more mindful about it. They just recognize it more, and I think they also can control it. When I know what makes my heart rate go slower or go down, maybe breathing calmly, maybe just looking at some things, just having this ability to see things and recognize things as always, and I've been talking about that for trillions of times, I think is the first step to being able to change something about that. When I know I do this, that, and the other thing, and then my heart goes down, or I feel a certain way, I can do something about it. But when I don't know about it, then I can't use it, I can't leverage this information because I don't have the information. So, and it kind of also underlines the whole mind and body connection, even though in this sense, is it then really a connection and not just, okay, I know my body very well, and so I'm using this knowledge of my body and, get it into a different topic. I get it into the topic of my mind and my mood. But there is a connection. I think it becomes quite clear, people that, maybe actually also in the way of just this lane that, or this road that is having two lanes, one down and one up. So when what did I want to say? Fuck. When I'm when I'm exercising? No, not when I'm exercising. Well, I don't know what I want to say. It was actually something quite good, to be honest. Let's see. Let's see if there's something else that prefrontal cortex and cognitive control. Yeah, maybe.
Immediate stimulation for getting into these networks. And I also just want to take a brief tangent and say, because I've heard you say this before, I think it's so vital what you're saying, that it's really not about stimulation of areas, or any specific brain area or vagus nerve being important per se. It's really about a network, a connection, a series of connections. I think that's really important for people to understand, and is kind of a new emerging theme, really. Yeah. The other thing that to me seems extremely important for us to consider is what are these lateral prefrontal cortices doing? Are they involved, for instance, in sensation, sensing the heart rate? Are they involved in?
And also, as far as I know, meditation does build gray matter, I think. Might be wrong there, but I'm going to look it up then. And might also affect the prefrontal cortex specifically. But I would have to look it up again and confirm that.
Thinking and planning. And this gets down to a very simple question that I know a lot of people have, which is, can we talk ourselves out of depression if it's mild? Can we talk ourselves into a manic state or an excited state, a positively excited state that doesn't qualify as mania? Other areas of the brain I think of is responsible for perception or for motor control. But here we are in this mysterious frontal cortex area, which people say executive function, planning, etc. Are we talking about thoughts? Are we talking about structured thoughts? Or are we talking about dreamlike thoughts? What in the world is going on in the prefrontal cortex? And here I spent my career, in neuroscience, and I still can't really understand what it's doing, and maybe it's doing 50 things.
Yeah, no, it's a great question. So, so one of the studies that we've been working on, in addition to the depression work, is actually trying to change trait hypnotizability. So David Spiegel and I have been working on this, and he's found and published this 10 years ago that a different part of the left dorsolateral is functionally connected with the dorsal anterior cingulate, with a lot of functional connectivity in high hypnotizables and not much in low hypnotizables. And that's a different sub-region within this bigger brain region we call left dorsolateral prefrontal cortex than the part that seems to be important for regulating mood. And so the left dorsolateral seems to have connections that are location specific within the overall kind of named brain region that connect to various parts of the cingulate and seem to regulate it, right? And so if you knock out the left dorsolateral prefrontal cortex and you have people do the Stroop task, for instance, which is a task where it's a simple task, you probably know this, you have people name the color of words. And so if I look at if I look at one of the cards that they'll show you, it'll have the word red in red, and that's very easy, and that's called a congruent. And then the incongruent is red in the color blue, and you have to say the word, you don't name the color.
So you have to suppress a response.
Yeah, exactly. And so I'm sorry, you name the color and you see the word written in a different way. And so basically, if you stimulate in a way that inhibits the left dorsolateral prefrontal cortex, or either one, you can actually knock out the ability to do that well, and it'll take longer for people on the incongruent cards to be able to name it. And so they have a kind of a time delay that's greater than they had before they got stimulated. So that's a part of the prefrontal cortex that's different than the part of the prefrontal cortex that's involved in mood regulation. The nice thing about TMS is that you can go through and you can find these areas that are functionally defined through brain imaging, and you can perturb them and answer the question you're talking about. How do I understand this part of the prefrontal cortex and its function, this part? And so we were able to stimulate in an inhibitory way within the left dorsolateral prefrontal cortex that's involved with, this sort of cognitive control area, and we were able to knock that area out and increase trait hypnotizability. So people had greater hypnotizability after they got active stimulation versus when they got sham. And so it suggests that brain circuit is involved in the process of what therapeutic hypnosis ends up being. But it's a very different region within the left dorsolateral than, say, we do when we do these very intensive stimulation approaches to treat severe depression, and we're able to get people out of depression. With the part of the dorsolateral that seems to be lower in the kind of more lateral and inferior on the DLPFC, and connected with this subgenual anterior cingulate, so the part of the anterior cingulate that processes emotion.
I'd like to take a quick break and acknowledge
Athletic Greens, AG1. Apparently that's the new name. But yeah, this is going to be it with the episode. It's already quite long as far as I can see, can judge that. I quickly, while I'm doing the outro, I really hope that I've been able, or at least Andrew was able to point out and or shine some light onto ideas, thoughts, maybe then also techniques, so things you could be doing to feel better, to work on certain things. And with that being said, I wish you the best and hopefully see you soon. And I was just Googling something. I'm sorry. So how does meditation affect the prefrontal cortex? Studies show that regular meditation thickens your prefrontal cortex, prevents it from shrinking with age, and also improves its connection with other areas of the brain, like the amygdala, helping you regulate emotions better. Yada, yada, yada. Of course, taking this with a grain of salt, even though they say like studies have shown and whatever, cool, nice, whatever. Just show me the studies and I want to read them on my own. But just pointing it out for further shining lights on ideas, thoughts, potential wisdom, and whatever. But yeah, I'm hopefully going to see you next time. So have a good day. Bye-bye.